A heat pump can deliver more heat to a building than the electrical energy it consumes because it moves environmental heat rather than creating all of it electrically. Electricity powers the compressor and auxiliaries while additional thermal energy is collected from air, ground, or water. That is why a coefficient of performance can be greater than 1 without violating conservation of energy. Delivered heat equals electrical input plus heat gathered from the environment. Energy is not being created from nothing. A heat pump is closer to a refrigerator running in reverse than to a simple resistance heater. The refrigeration circuit uses a fluid designed to evaporate and condense at useful temperatures and pressures. At low pressure it absorbs heat while evaporating. After compression it can condense at a higher temperature and release heat indoors. Changing pressure lets the system move heat from a colder source to a warmer destination. Refrigerants have environmental, safety and engineering trade-offs, so systems are designed around specific fluids. Phase change lets the refrigerant act as a practical heat transport medium. Moving heat uphill in temperature requires work, and the compressor supplies most of that work. Compressing refrigerant vapor raises its pressure and temperature so it can release heat into a warmer heating circuit. Compressor efficiency and pressure ratio strongly influence total electrical consumption. Fans, pumps, defrost cycles and controls also use electricity, so whole system performance is broader than the compressor. The farther the temperature lift, the harder the compressor generally has to work. Heat pumps generally work more efficiently with a warmer heat source and a lower required heating water temperature. A smaller temperature difference means the refrigeration cycle needs less compression work for each unit of heat moved. Large radiators, underfloor heating, and good insulation can help by allowing lower water temperatures. Existing buildings can still use heat pumps, but emitter sizing, controls, and heat loss need to be assessed. Heat pump performance belongs to the whole heating system, not just the outdoor box. Outdoor air below freezing still contains thermal energy that an air source heat pump can collect. The evaporator operates at a refrigerant temperature even lower than the outdoor air, allowing heat to flow into the circuit. Capacity and efficiency can decline as outdoor temperature falls, but suitable systems continue operating in winter. Performance limits vary by model and climate, so design data matters more than one headline efficiency number. Cold air is not the absence of heat, the refrigerant simply has to be colder than the source. In cold damp weather, moisture can freeze on the outdoor heat exchanger. The unit periodically changes operation to send heat to the outdoor coil and melt the frost. Defrost temporarily reduces useful heating output and consumes energy, affecting seasonal efficiency. Frost behavior depends on humidity, temperature, coil design, and controls, not just outdoor temperature. Seasonal performance includes messy real weather effects that a single laboratory rating cannot capture. Coefficient of performance is useful heat delivered divided by electricity consumed over a defined operating condition or period. A COP of 3 means roughly 3 units of heat delivered for 1 unit of electrical input under those stated conditions. Seasonal metrics average changing weather, water temperatures, and operating states for a more realistic picture. Comparing COP numbers without checking test conditions can be misleading. The better question is how efficiently the complete system runs across the heating season. A high-quality heat pump can perform poorly if it is badly sized, controlled, or connected to unsuitable emitters. Short cycling, excessive flow temperatures and poor hydraulic design push operation away from efficient conditions. Heat loss calculations, commissioning and control settings therefore matter as much as the equipment specification. There is no universal retrofit recipe because buildings, climates, and existing systems differ. Heat pumps are efficient machines, but successful heat pump heating is a system design job.